How many times have you printed something where the color looks great on your computer screen, then looks totally different once you print it? Welcome to the world of color printing. Whether you are new to color printing or have been printing on color devices for a while, this is something every operator will experience at some point in their career. In this brief presentation, we will explain the basics behind why this happens. Let's take a look. In a perfect world, choosing a color and printing it would be as simple as it sounds. In reality, successful color printing requires knowledge of color science, experience in the printing process, and the right hardware and software. Whether you want to produce a flyer, t-shirt, poster, or brochure, the process for printing in color contains challenges for getting the color right. It's not just a matter of choosing the color you want, but of choosing colors your output device can print. There are 4 basic questions to answer to understand the challenges inherent in color printing. What is color? How does the information about color move from stage to stage in the printing process? What factors influence how output color appears to us? And what can we do to make color more predictable? By the end of this presentation, you will be able to answer these questions and as a result, have a much better understanding of the process of color printing. So, what is color? Color is our brain's interpretation of different wavelengths of light. But what exactly is light? Light comes from the sun. The sun emits streams of energy in the form of billions of electromagnetic radiation waves of different sizes. In the middle of the range of wavelengths is a small band that we can see with our eyes. This is called visible light. Most of the time, this band of electromagnetic energy appears to us as white light. White light is a continuum of wavelengths discernible to our eyes as 7 distinct colors: red, orange, yellow, green, blue, indigo, and violet, sometimes referred to as Roy G. Biv. Sir Isaac Newton discovered that a prism could be used to split white light into these discernible colors. All objects emit, reflect, or absorb wavelengths of light. The color that we perceive an object to be depends on the physical characteristics of the object and which wavelengths of light it emits, reflects, or absorbs. The brain interprets simultaneous RGB, red, green, blue wavelengths as other colors. You perceive purple because the brain has translated a particular intensity of red and blue light together as purple. An apple appears red because the surface of the apple absorbs blue and green light and reflects red. To some degree, the perception of color is subjective. If you ask any 2 people what color something is, they are likely to have different opinions. Mood, age, capability of the eye, cultural and psychological factors all affect how we see or interpret colors. Now let's talk about the different sets of colors. Primary colors are those colors from which all other colors can be made. Secondary colors are made from combining these primary colors. What you may not realize is that the primary colors we use for oil painting are not the same as the primary colors used for working in other media. There are 3 sets of primary colors: painter's primaries, red, blue, yellow; light primaries, red, green, blue; and printer's primaries, cyan, magenta, yellow. The light primaries and printer primaries are the sets of colors that are part of the printing process, so we'll focus on these. Devices that emit light, such as monitors, televisions, and projection systems, use only 3 colors, red, blue, and green, RGB, to create all other colors. These primaries are called additive or display primaries. Secondary colors, cyan, magenta, and yellow, CMY, are created by adding 2 primary colors. Thus, cyan is created from blue and green, magenta from red and blue, and yellow from red and green. When all 3 display primaries are added together, the result is white light. Thus, white light contains all colors within it. Black is the absence of light, and therefore color. Devices such as printers create images from chemical pigments, such as inks, dyes, or toners. These devices use subtractive primaries, cyan, magenta, and yellow, CMY. Subtractive primaries are also called process primaries. The secondary colors are red, green, and blue, RGB. Red is created from magenta and yellow, green is created from cyan and yellow, and blue is created from cyan and magenta. Notice that the additive primary colors are the subtractive secondary colors, and vice versa. Remember that additive color was created when lights were added together. Subtractive color works in a different way. Subtractive colors are created from light reflected from a surface. Pigments absorb, or subtract, some colors and reflect others. Seeing a color in a pigment, such as red, means that red light has been reflected, and the other RGB colors, blue and green, have been absorbed or subtracted by the surface. Secondary printers' colors are all darker than the printer's primaries because when you add inks, dyes, or toners to one another, the result is a darker pigment. When all of the subtractive primaries are added together, the result is black pigment. Thus, black pigment contains all colors within it. All light is absorbed, none is reflected. White is the absence of pigment. No light is absorbed, all light is reflected. In reality, the imperfections in inks, dyes, and toners make the combination of CMY result in a color more like muddy brown. To compensate, black is added to the three subtractive primaries to yield CMYK, where K stands for black. CMYK are the colors of the four-color process. Before we go further, let's discuss a few terms that are used to describe colors. The name we give to a color, such as green, orange, or purple, is that color's hue. Any given hue can be made lighter or darker, which is called a hue's value or brightness. Sea green and pale green are both values of the hue green. When you add white to a hue, it is called a tint. When you add black to a hue, it is called a shade. A hue can range from its most colorful or most intense to gray. This range is the color's saturation. Highly saturated colors are their most colorful. Desaturated colors are closer to gray. Not all colors have hue. White, black, and all shades of gray are called neutral colors. This color space model depicts three dimensions: hue, value, and saturation. Everything in the physical world that can either perceive or produce color has limitations in its ability to encompass the entire range of possible colors. Each device used in a print process has its own range of colors that it can produce, called a color gamut. The larger the gamut for a device, the more colors it can produce. Rendering intents determine how out-of-gamut colors are converted from one color space to another. Spot colors are special colors produced by companies such as Pantone. These inks enlarge the printable color gamut, especially in saturated oranges and purples, as shown in the chromaticity diagram. Spot colors also include metallic and fluorescent colors. So, what are the practical implications of these different color sets? The different types of equipment used during the printing process, light-emitting devices like monitors and pigment-producing devices like printers, present a key challenge for matching colors between different kinds of devices. This is one of the reasons why a printed job might look different than it does on a monitor. It's possible to view colors on the monitor that you cannot print on your printer. Conversely, a color created with custom ink may be outside the gamut of colors for a monitor. The gamut for one printer will be different than the gamut for another printer. Therefore, the colors in a document printed on two different printers may not match. Now that you understand more about color, let's look at how color data moves from stage to stage in the printing process. There are at least 5 places in the printing process where color data can be converted, manipulated, or approved. Scanning to a digital image, viewing the digital image on a monitor, proofing the job, making color adjustments, and printing the job. Some of these are obvious areas where color may change, such as printing the job and making color adjustments. Let's take a closer look at some of the less obvious places where color may change. After an image is scanned into a file, it is displayed on the monitor. Does the monitor give an accurate representation of the image? Remember, devices that emit light, such as monitors and scanners, use an RGB to produce images. However, the technology used to capture the image in the scanner is different than the technology used to display the image on the monitor, which means this is an opportunity for colors to shift. One problem with using RGB models to describe a color is that color is often inconsistent between RGB devices such as monitors, scanners, and televisions. All monitor manufacturers use the RGB model for producing colors. RGB is device-dependent, meaning that manufacturers define their own colors for their devices. One manufacturer's red is different from another's. This is evident when you go into a television showroom and notice that the colors on the screens are very different. What does this mean for the user? Suppose you have chosen magenta for your company logo as seen on your office monitor. When viewed on another monitor in the office, the logo appears to be hot pink. When you look at the logo on your home monitor, it appears more purplish. It makes it hard to predict which color will appear on the final output. This is where a proof of the job to be printed comes in handy, so you can see how the printed output looks and whether or not you need to do any color manipulation to get it closer to the final desired output. Let's look at how the image of the parrot looks on the printer's monitor. So what happens when a print-ready file gets to the printer? A color printer includes software that reads the print-ready file. The software creates 4 separate maps or patterns of dots called raster images for each page of output. The process of creating raster images is referred to as raster image processing, or RIP. The raster images are created for each CMYK color. These are called color separations. The parrot is a continuous tones image called contone. During the RIP, contones are converted to halftone dots for printing, which then becomes part of the color separations. The pattern in which halftone dots are arranged is called a halftone screen. The dots vary in size to give the effect of lighter and darker colors. Halftone screens are characterized by the angle and the size of the dots. This is known as dot area. On the press sheet, the density of a color is controlled by dot area, the area covered by dots of ink expressed as a percentage. An image consisting of variable dot areas is called a halftone. The halftone dots for each CMYK color are laid down at different angles. The result is a blending of dots into a rosette pattern, which the eye perceives as continuous. As the paper moves through the printer, each color is laid down in a pattern of dots specified by its respective color separation. When the angles are off, the rosettes do not form. Instead, undesirable dot patterns called moire form on the page. During the RIP, the printer uses a color rendering dictionary, CRD, to convert the RGB values into CMYK data. Thus, here is another area where the color may change. At this point, we've covered what is color and the areas in the printing process where color may change. Let's take a moment to review. Devices that produce color from pigments, dyes, or toners use a subtractive model of color to produce images. These devices lay down varying amounts of subtractive primaries, CMYK, on the surface in the form of dots. Subtractive models for creating color are also device-dependent because the various manufacturers of printing devices and their associated toners, dyes, or inks use their own specifications for defining color. Printing devices can have very different color gamuts, and as we already discovered, printer gamuts can be very different from monitor gamuts. Thus, a shade of green seen on your monitor may show up as a bluish green on your inkjet printer and a turquoise on your color laser printer. Now let's look at factors that influence how output color appears to us. There are several factors that can affect color and clarity of printed output beyond what we have covered so far. The surface of the paper the job is printed on, the color of the ambient light source, and the subjectivity of our human perception all affect our perception of color. Colors do not look the same under different lighting conditions. A color that looks bright and vibrant under white light may look dull and washed out under colored light. It is important to use a consistent light source when proofing colors. If the final output is to be viewed under colored light, the colored light may drastically alter the appearance of the document and should therefore be considered in its design. Colors are also strongly influenced by their surroundings. We perceive a color differently depending on the background. This is called the adjacency effect. Note how different the blue center rectangles look against different background colors. We are less able to differentiate between colors if the colored object we are viewing is small. This is what happens when we buy paint chosen from a paint chip sample card and are surprised at how different it looks when the much larger painted object is viewed against other background colors. In the printing environment, using color inks, dyes, or toners on colored paper will yield a different result than using the same pigment on white paper. For example, some of the vibrancy of navy blue text will be altered if it is printed on goldenrod paper. Paper with an off-white or gray cast will reduce image quality. The type of paper stock used has an important effect on the appearance of the final document. Paper finish, brightness, and surface texture alter the perception of color and its sharpness. White paper with a smooth surface provides the best base material for printing high-quality output. Use of paper with color variations, such as parchment, will alter the image quality. Paper with a rough surface does not absorb toner well, and image quality is reduced. All paper absorbs the ink or toner in such a way that the dots spread out. This effect is called dot gain and can alter both the color and image quality of a document. Some paper, such as newsprint, absorbs a great deal of the ink. A few of the causes of dot gain are paper absorbency, ink or toner quality, and capabilities of the printing device. If we consider all stages in the printing process in which color can be altered, it sounds almost impossible to get the color we want. In reality, there are several things we can do to achieve desirable color. The term we use to describe the steps taken to predict and control color in printing is called color management. There are three factors that we can manage to make color more predictable: calibration, conversion, and characterization. Sometimes these three factors are called the 3 C's. One of the elements in the unpredictability in output colors is a deterioration in the performance of the input and output devices. Over time, input and output devices begin to perform outside the parameters within which they were designed. They require a tune-up, much like a guitar requires tuning to produce its best music. The age of a scanner, the software settings, and the conditions of the analog to digital converter technologies affect how it performs. The age of a monitor and how the settings are adjusted are just a few things that affect how it performs. The type of paper used in a printer, the toners, alignment, registration, and the density of the dots are just a few things that affect how a printer performs. This deterioration can be fixed by a process known as calibration. Calibration is measuring and adjusting the performance of a device so that it performs as the manufacturer intended. A properly calibrated machine helps us predict the output colors because we know it is performing as it should be, as measured against the standards the manufacturer set for that device. Every time an image moves from one device to another, a conversion is done to translate the colors of one device to colors of another. For example, a conversion is done when an image is transferred from a scanner to a monitor, the RGB to RGB color model, and from a monitor to a printer, the RGB to CMYK model. Since all device gamuts are different, the conversion process must redefine any colors that fall outside the gamut to fit within it. The colors that appear in a photo will be compressed into a smaller gamut that is within the gamut of your scanner. This will happen again as the scanner data is converted into data for your monitor and again at the printer. Conversion is done by software utilities within various devices. During the printer RIP process, for example, RGB values are translated into CMYK values. Conversion from RGB to CMYK can also be done at the PC. We know that RGB and CMYK color models are device-dependent, and that such models can result in inconsistent color conversions. To overcome this, new perceptual models of color were created. Perceptual models are based on how the human eye sees color. The Commission Internationale de l'Éclairage, CIE, was formed to study human perception of color and to set the standards for the measurement of color. CIE standards have become accepted internationally. Two common CIE models are CIE YXY and CIE LAB. Each defines a color mathematically. These color models are device-independent and can be used by any manufacturer as a standard against which color can be measured. The usefulness of device-independent color models is that they increase the predictability of color as it moves from device to device. This is done by converting, for example, RGB values to CIE color space values and then into CMYK values. The color gamut of a device is expressed as data in a digital file, called a device profile. Characterization is how we describe the color gamuts for devices. For example, EFI Color Extension for Quark Express and ColorSync 2 are applications for the Macintosh computer that contain device profiles for a number of different manufacturers of monitors, scanners, and printers. The profile for a device must be created by the manufacturer for correctly calibrated machines. It is important to set expectations. There are many factors in color reproduction that can yield unexpected color results, and these are no fault of the operator, manufacturer, or software. The best defense against unpredictable color is an understanding of the complexities of the color printing process and exerting influence over the points at which you do have control. Color management is the best answer we have for creating predictable color and involves calibrating devices so that they work at peak performance, converting the data when color moves from device to device using device-independent models, and characterizing the color gamuts of each device. Color management systems, CMSs, are an evolving breed of software applications. They give us the best control we can get. CMSs are software applications that help us to do the job of color management. A CMS coordinates the device profiles of many different devices so that color is reproduced on screen or in print in a consistent way. It adjusts the color of an image on a monitor to approximate the corresponding color within the gamut of the output device. To do this, a CMS depends on device-independent color models. Now you should have a much better understanding of the complexities of the color printing process to know exactly where color can go astray. Let's review the specific stages in the printing process where color is approved, manipulated, converted, and viewed. Perception of color is somewhat subjective. Mood, age, capability of the eye, cultural and psychological factors all affect how we see colors. Scanners, monitors, and printers use different models for creating color. Monitors and scanners use an additive RGB model for light, and printers use a subtractive CMYK model for pigment. Manufacturers use their own definitions for creating color. The colors seen on monitors and printers are device-dependent. Device-dependent models are often inconsistent between devices. Each device has a range of colors it can produce called a color gamut. This range defines the limits for that device. The vivid blue seen on your monitor may be outside the color gamut of your printer. The fabulous color of your orange t-shirt may not be a color that your monitor can create. An image may undergo color adjustments during the print process. The conversion of an image's color data for each succeeding device in the production print process may cause variation from the original colors. One of the places this happens is at the RIP. The devices in the printing process have to be properly calibrated so that they consistently yield their intended color output. The paper color or texture can affect the appearance of color images and the color of text on the page. And the light of the surrounding area influences how the colors appear to us. Now that you have a better understanding of color science basics and how they apply to color printing, you should understand why a printed job may look different from how it looked on your monitor. By applying the knowledge of color science and using the tools and software available to help manage color, you can definitely achieve consistent, repeatable, and expected color output.